tema también sumamente interesante sobre lo que es toma de decisiones. Está conosco o mestre Jorge Alves. Fala espanhol.
Hello, ok. Espanhol é um pouco mais difícil, né? Eu prefiro...
Inglês, é melhor inglês?
É melhor inglês, eu acho. Eu consigo entender bem vocês, mas eu acho que para eu me expressar em espanhol não vai dar certo.
Pronto, então inglês. Muito bem.
Okay.
Very good. Then, good afternoon, everybody, once again. We will listen to Master Jorge Alves. Jorge Amaral Alves, Master in Electrical Engineering Signal Processing at Federal University of Rio de Janeiro, Master in Computer Science at Naval Postgraduate School. He worked in electronic warfare at the Brazilian Navy Research Institute, and nowadays he is teacher at the head of the electronic department at the Brazilian Navy Academy. Am I right? And yes, he's also captain of the Brazilian Navy, right?
Yeah.
Welcome, Master Alves, and they are all yours.
Okay, thank you very much for your introduction. And good evening to everyone. I hope that you enjoyed my simple presentation, but it's really a pleasure for me to be here presenting the work that we've been doing in some years. May I share the screen with everybody and start? Okay.
Sure, yeah.
That's right. Okay. Okay. That's okay. Everybody is seeing my first slide?
We can see your presentation.
Okay, thank you very much. So as you can see by the introduction, I'm a captain of the Brazilian Navy, and I've been working on electronic warfare systems and also on the processing techniques in order to detect mostly the modern radars. Okay, we started with the simple models, the first generation, and we say that. But now we are going to another step, and this work is about this. Okay, so I'm presenting the importance of electrical engineering intelligence, in the estimation and parameterization of electromagnetic pulses detected by electronic warfare support measures. Okay, let's see what does it means. The authors, I'm here, or Amaral Alves. Okay. I will be presenting this sequence. First, the contextualization that I will spend some time in order to show everybody and try to level the knowledge about this, because I know that it's a Navy team, but I'll try to explain. I'll show the main theoretical framework. That means how the radars are still working nowadays. The modern radars are using the techniques they are using, and mostly the math tools that we need nowadays in order to detect these modern radars. That's the sequence. Okay, and the results, you will see that the results are visible. Okay, are images, and we can, that's the reason, because in the future we intend to turn these images into parameters that can be analyzed in the future in the automatic way. That's the way it goes. Okay, and then I will show you how it works in the Brazilian Navy as a program, future program. Just another two example. This is a Chinese ballistic missile that was launched in 2020. in November 17. And the idea here is that they are in the nose of this missile, they use an active radar that is a modern radar. And the modern radar that we mentioned can be compared in these two lines here, okay? The red line and the blue line here. What is the difference? Normally, in the Second World War, we used the conventional pulsed radars, okay? The idea is simple. You just transmit a high peak power during a small time, okay, period of time. And the idea is that we can detect, that this table is showing us this, it can detect 100 square meters straight section. It would be a destroyer, a bear shunt, something like that, okay, in 25 kilometers of distance of your equipment. Let's say that again. When we say that we are working on electronic intelligence, we are on the other vessel, okay? One vessel has the radar, but you are at the other. So you have a receiver, not a transmitter, okay? Who has the transmitter is the radar ship, the radar missile, for instance. But we are here, we are the target, and we want to detect the proximity of the missile. So we need to detect the radar, that the electromagnetic wave that is being transmitted. So these two lines here shows this. We can detect in the if the enemy, the Chinese here is using in this missile a Second World War radar, we could detect it at 25 kilometers of distance. Okay, but that's not the truth. The truth is that they are changing the power being transmitted. And for instance, if you are using here 1 milliwatt of power, you can only detect it at 5 kilometers. So it's you can do nothing against this. That's the difficult part. Okay. Also, if we have a missile, a small one, you will have 1 square meter of straight section, okay, cross section, and you will have a little less time to react. That's the idea. So the idea of this table is just to show us how the things changed from the Second World War to modern world. Okay, and let's see in another way how it works. When we say a Second World War radar, we are talking about high peak and a small period of time of transmission. And that's the way the receiver will see. So what we need in a receiver, we just a very sensitive one, okay? A sensible, a high sensitivity receiver. That's the way we can detect this radar being transmitted. So that's how it works for a long time. But the radars, the modern radars, are changing to a low instantaneous peak power and during a continuous period of time. Okay, this is the most time. It could be like we say this kind of behavior is from a low frequency, a linear frequency modulation radar. That means you have a sweep of the radar, and during the whole time it's transmitting. Okay, it's never stops. So it's the highest part. But the energy are the same. That's the idea. Okay, we have here the same energy of this one. The difficult part is how a receiver will try to discover or detect this little power here, because you have also the noise, okay, the white noise in the behavior. So we cannot, the point is, we cannot use time domain. Okay, we have to go to a spectral domain in order to find real signals that are being transmitted. That's how the modern radars are working. Well, these radars are using, for instance, that is one on Navy ship here, and the radar is here, and how it works nowadays. It if it was the Second World War, it would be like this one, okay? A high peak, okay, of energy in a short period of time. But what they did, they just divide this one by 10, for instance, or by 1, 2, 3, 6, 9, okay? 9 pieces. We instead of transmitting one high peak level pulse, we are transmitting 9 low peak power pulses, okay? And what the consequence of this? The consequence is that if you have a receiver, ESM receiver, electronic support measure receiver, as we say in English, we will not be able to detect it by amplitude. If you put it in an oscilloscope, you will not distinguish between the noise, because the noise level is above the pulse. Okay, so the noise received by the ESM, it will not be able to distinguish between both of them. So that's not the way. We cannot work with this kind of radar using time domain. So that's the point. We go to our spectral domain. These are the tools we used in our program. What was the idea? As we worked in academic way, because electronic warfare is a very sensitive subject, we simulated the signals. Okay, so we simulated the radar signals using the Barker codes or Frank codes, or simply linear frequency modulation. That is very simple to understand. That we keep the same power, okay, the same power, but we change the frequency of the signal during a period of time. So it's a kind of pulse signal, but with a low power peak. Okay, that's the idea. And also we use these two codes here because the behavior in the spectrum, because what we will do, we will get these signals in time domain, and then we'll change to our spectral domain, frequency spectral domain, and we'll be able to see the difference between the codes. Okay, so the Barker code is very well known. It depends on the length of the Barker, okay? But mostly the modern radars are using the high number here, 13, 15, 11 possible. This kind of 0 degree or 108. So it's the idea of plus, 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 minus, minus. It's just shifting on the frequency, okay? On the phase. You have the 0 degrees as one phase. This is the sample of the signal. So you have one sinusoid signal. You sample it, or 4 times, 2 times here, or 13 times, and you add a phase. Okay, 0 degree or 108 degree. That's the idea of the Barker code. Similarly, it happens with Frank codes, but the analysis is a little bit more mathematical, but the idea is the same. Okay, you find the phases that you have to add to the signal in order to code with the Frank code. And the linear is the simplest one. It's very simple to understand. Another thing that we did in this work was how we can try to simulate a better signal, better real signal, as we are using. We did our work in MATLAB, okay? So it's really an academic study. It's not a real-time development, but the idea is to add noise to the signal in order to approach the real situation. And we did this additive white noise, and we added it to the transmitted signal and see if our algorithm was robust enough to reject the noise. That's the idea. And in this way, as we are dealing with signals corrupted with noise, we need to use autocorrelation. Okay, the autocorrelation was a useful tool in order to reject the noise, because we are dealing with white noise in most of the time. In real behaviors, we are dealing with white noise. So autocorrelation was the good choice for us, at least. And the idea is, when we pass the autocorrelation function to a signal that has white noise added to it, we get the real signal instead of, we filter the noise. That's the purpose of autocorrelation. Okay. The other tool that we used was the short time Fourier transform. Okay, let's see what does it mean. The idea, you have the time x, okay, and here the frequency x, and the other x here, you have the amplitude. So how we interpret, how we analyze this draw here? Well, we have here one pulse in 300 hertz. Okay, that's what's showing us. So at time 0 until time, I don't know, 10 here, we have one pulse that is located, is transmitted, and it's being transmitted in 300 hertz. After that, this radar is transmitting another pulse in 200 hertz, okay, during this short period of time, and then another third pulse, okay, in maybe 100 hertz, and the fourth pulse here could have 50 hertz, and would be our last pulse. So it would be a radar that is transmitting 4 pulses at a time during this period of transmission. That's the way we could analyze this draw here, this picture here. Okay, it's not the real one, of course, because when we talk about radar, we are not talking about low frequency. We are dealing with gigahertz frequency. But that's the example that we can understand why we are using the short time Fourier transform in our work. Okay. Well, let's see. These are our results. Okay, the first one here is the simple one, is the time domain signal added with noise. Okay, what we can understand here, this would be our sweep. Okay, this period of time would be this whole window here. Okay, we have this small time here with no transmission, then no transmission, only noise. Okay, this whole picture here. We only have the carrier that we are transmitting during this short period of time. So this is one simple pulsed radar signal. Okay, this is what we see in a time domain. But if we do a spectral domain analysis, for instance, if we calculate the autocorrelation of this signal and also the short time Fourier transform of this signal, we get these two pictures here. Okay, this fourth here is just a cut, horizontal cut of this 3D picture. It's easier for us to see from above. Okay, as we could see above this 3D picture, we would get this kind of image. And what is showing us, that's the idea. Here we have the time, so I know that I have one pulse signal during this short period of time here, between half second to 1 second, and the frequency is changing from 1.6 to 1.8 gigahertz. Okay, so that's the importance of calculating or getting the short time Fourier transform. And then after we get this, we do a spectrogram. That's the name of this picture here. We just do a cut, horizontal cut of the 3D picture here. And with these pictures here, it will be able to see what is the code that the radar is transmitting. Let's try to understand why we need this. We need this in order to identify the radar. That's the purpose of all the job. I want to know if the radar that is reaching my receiver is a Barker code radar, is a Frank code radar, is a linear frequency modulated radar. That's the purpose, okay? And we can do this using the autocorrelation and the short Fourier transform. That's the results that we will get, okay? How we can prove that it's true? Well, the first one here is the spectrogram that we get when the signal being transmitted is a linear frequency modulated during a period of time, okay? It's not, we have another kind of radar that we say it's a continuous wave linear frequency modulated. It would be like this one, okay? Here we have the sweep of the radar, okay? The whole time it's transmitting. It has a linear frequency increasing, okay? It's coming from 1.6 to 1.8 during the whole sweep time. That's the difference between the linear frequency modulated continuous wave radar to a linear frequency modulated pulsed wave radar. It's this one here, we have the sweep of the radar that's all of this, but this one is the only piece of time that we have the pulse, okay? And the pulse is changing its frequency from 1.6 to 1.8, okay? That's what we get when we do the short time Fourier transform. So we can see that they are both very well distinguished, very well, it's easily to distinguish between them. This one here is a strange picture. This picture here we get when we have a radar signal that is coded with Barker code, okay? It's kind of an image that can be seen as two pieces, one up and down, and here with small nulls. So the idea here is that show to everybody that it's possible to make probably what we will do in the next future works. We do some techniques, image processing techniques, in order to automatically detect the different coded radars like that. Now, using some techniques, image processing techniques, I can distinguish very well both, all these four different images. Okay, I can treat them as images. This fourth one is what appears when we have the Frank code. Okay, when we have a radar signal coded with Frank and we do the short time Fourier transform, we get kind of two halves. Both of them are has an inclination. Okay, but one is starting with high energy, then it will decrease linearly, and the other one starts with low energy and then will increase. That's the behavior of Frank code. So in this image, we can see that it's possible to make some automatic techniques. That's the future. Okay. Another result that we get, it's easier to show everybody about the results. It's just the analyzing of the autocorrelation function. These three images here, the line below is just a zoom of the first line. Okay, this what we have here. We have Barker codes, different with different numbers. Okay, and we can detect exactly the Barker code 11, Barker code 7, just counting the number of main lobe and the lateral lobes. Okay, so the idea here, we have one main lobe, the center, and 6 lateral lobes. So we have here Barker 7. That's possible. We have we did this tests and we get this solution. Here we have 5 side lobes, more added to more 5 side lobes, and 1 main lobe. So we have here Barker 11, okay? And the last one is Barker 13, okay? 6, 6, 12, 1, 13. So this is another possibility of our work, is to get this also automatically. We can do this job also with image processing techniques. That's our future work. Another capacity of our system will be to detect between different, as we showed before, we are using the autocorrelation function to determine if we have Barker 7, 11, or 13. But we can also use the autocorrelation function to distinguish between Barker code, because always we will have this kind of comb peaks, okay? We have some peaks spaced, equally spaced in the spectrum. And when we have the autocorrelation of Frank code, we will get this kind of a different image here, where we have some side lobes that are small, and it doesn't have the same picture as this one. As we can see that we have one big peak in the center of our spectrum, but then we don't have the other peaks that we can get with the Barker codes, okay? And when we have the linear frequency modulated signal, we get this kind of spectrum here, where we get one increased behavior and then one decreased behavior. So it's also possible for us to get this parameterized in order to get it in an autonomous way, okay? And the last one is the analysis with the noise. It's very important for us to see or to show that our way to solve this problem of low probability of detection radars can be solved with this kind of analysis. Because when we have noise added to the signal, it's impossible to detect any pulse using the amplitude, okay? Here we have the signal and noise, but with signal noise ratio low, okay? Then we are increasing the signal to noise ratio, and this one is impossible for us to see the peak of the signal, okay? But if we do the autocorrelation, we get a clear spectrum, and so it's really strong enough for us to be applied in equipment, ESM equipment, okay? So that's the idea. This job is related to the development of a new generation ESM. We call the Brazilian Navy ESM that is installed in some of our frigates. It's called the Defensor, and we are developing the new one that will be MK3 in order to be installed in the new class of frigates that we call the Tamandaré frigates. They are still on development, and the idea is to get this ESM with this way to detect modern radars with compression techniques and also low probability of detection radars. The other possibility will be to install our future ESM equipment in our future submarine that also is being developed by Brazilian Navy. Okay, so I tried to be very fast and simple. I hope that everybody has understood my explanation. The point is, what we did was just to get the results in order to maintain the idea for the future, because what we need is to get the detection autonomy. Okay, so we will need to put a neural network working together with all these short-time Fourier transform results in order to get an automatic response for the detection of the modern radars. Okay, thank you very much for the audience. I'm here for any questions. Thank you very much.
Thank you, Master George. Questions or comments for Master George? Remember that we also have the channel, the YouTube channel and the platform Global UCR, where we can ask also questions in the forums. Mais uma vez, muito obrigado, Master Jorge Alves, pela palestra, muito interessante.
Muito obrigado pela oportunidade. Thank you very much.
Thank you. Si no tenemos preguntas o comentarios para Master George, por hoy este sería el cierre del bloque de la sesión temática de aplicaciones. Y si lo tengo, si estoy en lo cierto, mañana tenemos también 2 bloques en el mismo horario, desde las 14 hasta las 17, UTC-6, GMT-6, horario de Costa Rica. Tenemos un primer bloque de aplicaciones donde exponen el doctor Hugo Flores Arguedas, doctor Cuthberto Romero, doctor Roberto Duarte, y en el segundo bloque exponen la doctora Blanca Pérez, el doctor Walter Campos y el doctor Wilmer Palacios. Entonces, de mi parte, por hoy creo que sería todo. Y los invito cordialmente para que nos acompañen en la sesión temática de aplicaciones o en la sesión temática en la que tengan agrado el día de mañana. Muy feliz tarde. Boa tarde.
Boa tarde.
Good afternoon.